Hi, everybody, and welcome to the penultimate session of the Spectral Geometry in the Cloud seminar for 2024. So for this second last talk, we have Hanna Kim from the University of North Carolina, Chapel Hill, who will talk to us about upper bound of second Laplacian eigenvalue on the projective space. Hanna, the floor is yours.
Thank you. Hi, my name is Hanna Kim. Thank you for the organizers for inviting me for the seminar. Today I'll be talking about isoperimetric in a problem of the second Laplacian eigenvalue on the projective space. Some of the work is some of the talks today will be joint works with Richard Laugesen, who was my PhD advisor as well. So a little background is if you consider a n-dimensional closed manifold M, we say that there is a base metric G and its conformally equivalent metrics in the conformal class multiplied with W, which will be a conformal factor and works as a weight endowed on the manifold. Here, for denotation purposes, the metric will be normalized in the conformal class so that the volume within the conformal class stays always the same and equal to the base metric. This will get rid of, when we trying to maximize the eigenvalues, we have to normalize with this volume. This will get rid of that volume factor so that notation-wise, we just have to care about the eigenvalue. Here, if we consider a Laplace Beltrami operator on the manifold with a metric WG, we have a discrete sequence of eigenvalues. And first we begin with, of course, the zero eigenvalue because it's without the boundary. And then we have lambda 1 and lambda 2, and then increases to the infinity. Here, of course, the eigenvalues within the conformal class will depend on the conformal factor denoted as W. It will be the function of that. And today, I'll mainly focus on the eigenvalue of lambda 2 on RPN, otherwise rolled projective space. So the isoperimetric problem that I'm interested in is maximizing lambda 2 in the conformal class of round metric on RPN. So I'll mention some results of the sphere as well because it's related. And here, recall that our volume is normalized, so I'm just going to talk about lambda 2. I would also like to mention lambda 2 is essentially the third eigenvalue, but here I say the second eigenvalue because we always, I'm denoting 0 as my lambda 0. So the reason that we consider only the round metric for the sphere or projective space, and now my base metric G is just the induced metric, the reason is that it's known that outside the conformal class of round metrics, you can create a sequence of metrics that makes arbitrarily large lambda 1 in dimensions 3 and higher. So you can basically, if you think of a manifold, you create a little hole and then you attach a sphere and then you transfer all the weights to the sphere so that the manifold acts almost like the sphere. And then you can create like a good estimate of which the lower bound so that it becomes arbitrarily large. So that's why when you consider one conformal class, of course, when dimension is 3 and higher, we have infinitely many classes, but and then we restrict it to one class. Okay. Some of the related results in ascent is that for the first eigenvalue, in the 2 dimensions by Hirsch and all the higher dimensions, including 2, Al-Sufi and Elias showed that lambda 1 is maximized when the metric is round. And in this case, of course, it's equal to the dimension n. And as you can see that my weight is 1, so that it's equal to the base metric. And for 2, lambda 2, the second eigenvalue, Nadirashvili and Penskoi in 2 dimensions, and during my PhD, I was able to show that lambda 2 is maximized where the upper bound goes to, there is a sequence approaching to that of 2 disjoint union of two round unit spheres. And the reason it's a strict inequality because I'm considering the smooth ones, and there is a sequence of metric to it degenerates to a metric that's not as smooth. And the model that I'm thinking of is here is if you have a sphere like that, you create, you consider this small region and you endow big and big metric so that it becomes like a sphere. In the limit, you have 2 bubbles forming, and that is the upper bound that we're considering here. And there is a 2 over n exponent, and that's just because of the dimensions. And you can easily see that when n equals 2, it's going to be a 4. And other related results are for the first eigenvalue on RPN, when dimensions 2, Li and Yao showed, and also Elias showed that on the higher dimensions that, again, the upper bound is attained when the metric is round. So it's 2n plus 2. In this case, because one way to think about the real projective space nicely is you can think of it as like a hemisphere, and then you take the even eigenvalues of the sphere, and that's why you have 2n plus 2 as its first eigenvalue when the metric is round. For the second eigenvalue, so this is what I'm interested in higher dimensions. In RP2, Nadirashvili and Penskoi showed that the upper bound can be obtained by a sequence of metrics degenerating to a disjoint union of round projective space. So here I think of a hemisphere and a bubble forming on the side, a sphere basically with a different ratio of radii, say square root of 6 and square root of 2. So you might be wondering why such ratio. So they actually naturally come from the eigenvalues of the round metric. So in the case of the projective space, when you plug in n equals 2 here, you would have 6, and for the sphere, you would have 2. So that's where the ratio of the radii actually comes from. Okay, so what happens in the higher dimensions? And that's what I was interested when I was a grad student, and I had this conjecture that this bubbling phenomena will generalize nicely to higher dimensions as well. So that was my conjecture, that the upper bound can be obtained with a disjoint union of RP2, RPN, and SN, so that the ratio of the radii with the same 2n plus 2 and square root of n. Okay, as you can see, it's the sum of 2. And however, I was able to prove something weaker is that you actually get 2 projective spaces. In dimension 2, when you actually plug it in, this actually gives 12 instead of the 10, which was the sharper bound. Yeah, so what I'm picturing is as you can see, like something like this. Any questions so far about the results?
Yes, Anna, why do you say the geometry in the first case it was a bubbling, but this one is two hemisphere?
So are you asking about the conjecture too?
Well, I'm asking about the picture you just drew in the previous slide. It was a hemisphere and a sphere.
Yeah. So that is the case that I am picturing in my theorem, the weaker bound.
Okay, thank you.
Yeah. Okay, thank you. Okay, so I'll move on to the proof. So I use something that was very well established. So I want to find the upper bound using the Rayleigh quotients, so that if I have an eigenvalue depending on W, I use the variational characterization. Now I want to construct U so that it's orthogonal to the constant, which is the eigenvalue for the zero eigenfunction for the zero eigenvalue. And first eigenfunction, I'm going to call it first excited state because I'm referring to a specific eigenfunction of the metric WG, and I'm going to call it F. So I want to construct multiple of that and multiple of trial functions, and I'm going to average that later. Okay, so for the proof, we construct the trial functions. So this was very well established. I also used it in my sphere, and there are other works, including the works Gerard, Laugesen, Freitas, and constructing trial functions in this way. So I'm applying those similar ideas to this case as well. So how I build it is that you pick an RPN point Y in the projective space, and then you map it to higher dimensional sphere, which I'm going to call it SM-1. It depends on the original space dimension, which is n, but I'm going to explain later where this n comes from naturally. So what happens in the picture is that what these maps do is that you consider like a hemisphere RPN, and then you map it under phi. So it becomes like an embedded surface. So I'm drawing it as a line to show that it's an embedded surface in some higher dimensional sphere, SM-1, and then you fold it on the sphere of this embedded surface, and I'm gonna call it f of h. So what happens is this orange line gets folded across some spherical cap. So the spherical cap, denoted as h, depends on two parameters, which is you pick a point on the sphere, and then from there you scale the spherical cap by t, where t varies from 0 to 1. And when it's 0, it's going to be hemisphere, and when it's 1, it's going to be all sphere. So I'm only considering this. You can think of it as h, just the bigger spherical cap, and the other one is just a smaller spherical cap. So I'm considering what it means to be fold is that you define identity on this bigger spherical cap, and then you define the map as reflection across the spherical cap and denoted as R of h, R subscript h. And then you would have this two parts, right? This orange line now has two parts. And then what you do is use Mobius transformations restricted on the sphere, this higher dimensional sphere. And what this Mobius transformation does, you translate the masses. Basically, you pull all of the mass with respect to minus c. So as you can see here, you pull all of the mass towards minus c. Okay. And what it's gonna do, it's gonna create some symmetry that I'm gonna mention later in the pictures, and that's what it's gonna get us to the orthogonalities. Okay. And lastly, of course, because it's on the manifold, we have to map it back to the sphere using the spherical harmonics, where y is consistence of eigenfunctions of the round sphere. And I'm going to drop the work that follows. Okay. So all of these maps are well-established method, and I just wanted to explain what these maps are. And this phi is, I'm going to call it a generalized Veronese map. And the idea of constructing phi is based on the classic idea of isometric minimal immersions, sending surfaces two-dimensional manifolds to higher dimensional spheres. So some of the other examples, including the discussions of isometric minimal immersions, are some isoperimetric inequalities of lambda 1, you can think of it in torus and Klein bottle, and there's also result in Boltzmann surface. So people used it a lot, and Li and Yao also actually used it for RP2 to S4 and use this Veronese embedding and use the fact that it's a minimal immersions, and denote as phi2 here. And why do we consider this phi? Why is this map so useful, you might think, is that the reason is that sending RPN to higher dimensional sphere is crucial because I want to use this fold map and Mobius transformation to create some kind of symmetry, and they are actually just defined on the sphere. And so to use these tools, I wanted to use this map. I wanted to use the map phi so that it gets sent to the higher dimensional sphere. Okay, and another nice thing is that you can construct it very explicitly of this phi, is that because by Takahashi is that you can take the first eigenfunctions for the round metric, and with a conformal factor, it's not really accurate. It's actually a constant conformal factor related to eigenvalue, is that related to eigenvalues, and so we know explicitly how to construct it, and it's also minimal immersion. And one of the nice things about when it's a minimal immersions as well is that you can control your volume, how larger it gets under some diffeomorphism. So let's say F is some conformal diffeomorphisms on the sphere, and the pushward measure of, let's say phi is the minimal immersions, and then if you compose it with some F, right, and all of the volumes is controlled by the volume of phi pushed forward with G. So however you compose the maps, it's going to have an upper bound of the volume with some constant vector. So that's what it's nice about it. Okay. So how do I construct this Veronese maps is that I based on phi2, I was able to just construct it inductively. So I'm not gonna show you the formula because it's way too much. But when n equals 1, the phi1 is actually minus z. So if you consider like a complex plane, minus z bar square. So it actually makes sense because RP1 is like a half of this sphere, half of the circle. Okay, for dimensions higher, I define it inductively. And here, now I know what the higher dimensional sphere is, the dimension of the higher dimensional sphere is. That's just going to be the multiplicity of the eigenvalues of the first eigenfunctions. Okay, and we have some constant conformal factor related to eigenvalues. So after building that, I want to show that these maps actually work. So by that I mean these maps are actually valid trial functions. It's orthogonal to the eigenfunctions. So what I do is construct this vector field consisting of L1 multiplications of my trial functions with a constant function. So this is going to take care of the orthogonality to the constant, and the next part will be the multiplications of the first eigenfunctions with my trial functions. And I denote this vector field as V. And what happens is that it's going to depend on the parameters of my trial functions. So the first parameter being the parameter for the Mobius transformations. And for the spherical cap, I have P and T. So my goal to show the orthogonality is to show that this vector field is in fact going to vanish for some parameter. How I'm going to show is that when 0 and it's 1, so I'm going to just compare these two states. So I can consider this vector field like a homotopy, right? And what I'm going to compare along this homotopy is two states, is that if you consider when it's exactly 0, the spherical cap will be just a hemisphere. And what's going to happen is I have two curves going around looking like this. And I'm going to say that the degree of V in this case is non-zero. And when it goes to 1, what it's going to happen is the bigger cap will be larger and larger, right? And in the smaller cap, you're going to see that it's going to get reflected. And as you can see, the smaller part will get reflected to a larger and larger parts, right? And what's going to happen in the end is that the full map, define identity here, and reflection maps is that it's not going to depend on whatever direction that you have, because full map, it's just going to be identity map on all spheres. So it's going to be a constant because it does not depend on P. Okay, so then what's going to happen is that the degree is going to be constant. So the degree of this homotopy will be just 0. So it's going to vanish between t 0 and 1. And that's what I'm going to use. So to see that why that works, we first show that to go back to just equation solving, we compare the dimensions of the parameters and the conditions. So I have the trial functions, and the parameter, it comes from the classic idea by Hirsch that we can pick a center of mass so that we can create some kind of symmetry to make my trial functions orthogonal to the constant functions, constant eigenfunctions. But here in this proof, I don't really assume that it's a center of mass, but that's the basic idea. And also another trial functions have parameters of p and t, which depends on the parameter direction and the size. So it has a dimension of n as well. So, and it's going to create some kind of symmetry so that it's orthogonal to the first eigenfunctions. Okay. So I have m dimension of the conditions here, and my parameters each have m dimensions. So it match so that we can see that we have a hope of solving this equations. Yeah. Any questions? Okay. So.
I think I have a question. What is the role of the number of parameters? Why do you count them?
I want to count them so that my conditions and my parameters have the same dimensions. When I solve the equations, do we have a hope of solving?
Okay, thank you.
Yeah. So under a certain homeomorphism, so I'm going to change that the space of my parameters live basically are going to be on some odd-dimensional sphere. And I use this reflection symmetry to show that my degree is non-zero. And this proposition is similar to a result in Karpukhin and Stir. And what happens here is that if you have a self-map between odd-dimensional spheres, is that if you have a continuous map, and assume that we have this following reflection symmetry. So you have something, reflection map depends on these second parts of the sphere, in which I'm going to denote RB, and you consider this cross product of the reflection map. So what's happening is that when B is not equal to 0, you can define the reflection map. So it's same as if you apply reflection maps inside and if you apply it outside. When B equals 0, we cannot define the reflection map. So what we would have is that we would just have the identity. In that case, degree is not 0. Okay. So this theorem is actually, it comes from very classic idea of Borsuk-Ulam theorem, is that in the Borsuk-Ulam theorem, it says that, well, when you have a odd map from a sphere to sphere, your degree will be non-zero. And that's how I proved this proposition as well, using one of the proofs in Borsuk-Ulam's theorem. So I'll just show you because it gives like a good intuition of how we can see the degree, why the degree is odd. Is that, so you consider this higher dimensional ball, and what I'm going to do is I'm going to divide into two parts where the last coordinate of B, denoted as Bn plus 1, and the hyperplane of the whole space, denoted as R2n plus 1. And what I'm going to do is I'm going to expand my map defined on the sphere to inside. And what's interesting about the degrees is that you can compare the degrees of the ball with the degrees of the sphere, and they're actually, degrees of the ball at 0 is actually same as the degree of the sphere. And so let's look at this green part first. So I'm going to extend the map on this green part, and if you enlarge the green part, it's just going to be some higher dimensions, odd dimensions. And let's say for convenience, it's a 3 dimensions. Then what happens is I'm going to define the identity map in the small disk, right? And what happens in the smaller dimensions, you're also going to have identity here. And when B is 0, I can define, as I said, this is just going to be identity map. So I'm going to define all of this identity map on this blue part. And on the other parts, I'm just going to use some extension theorem, whatever that is, I don't care. And I'm going to extend it, and using the reflection symmetry, I would get another extension on the half annulus as well. Okay, so the same thing happens in the higher dimension, and then you build this like extension. And in the end, what's going to happen is you're going to have identity map on this region, and you're going to have something extended here, and by reflection symmetry, you're going to have something extended here. So I have three parts on my sphere, where the first part is going to have degree 1, and this part, the annulus part either cancel out the degree or they're going to be the same depending on the dimensions. So I'm going to have something 2n, 2k, let's say, because I'm using, yeah, so that's why we're having odd degrees. Okay, so now I know that this does not, so in fact, this vector field actually satisfies the reflection symmetry. So what it means that because it satisfies the reflection symmetry when t equals 0, it's gonna have a degree non-zero. So that's how I show that something's gonna disappear. This vector field will vanish at some point. Okay, so now I proved the orthogonality. Now I want to show that by plugging in this trial functions to the Rayleigh quotients, do I actually get the quantity? Substitute all of these trial functions the Rayleigh quotient, and then I multiply all of this denominator on the left-hand side. And using that, this is just a point on the sphere, sum of the denominators is equal to, the integrand will be just sum of them will be 1. So I'll just have the volume of my RPN, and as I said, I normalized the volume, so I would have just the volume of with conformal factor as 1. And I apply the Hölder's inequality, and this, I would get the right-hand side. This notation is just means that I consider all the gradients of each coordinate, and I just take the L2, a little L2 norm of the gradient. Okay, and then what I would do is, using the conformal invariance of the metric, my W will disappear, and then I use the conformal invariance of the maps using this Mobius transformation and fold map. So remember, the fold map consists of the two parts, so I have to consider two parts. So it divides into two parts, where I had RPN, and I push forward with phi, and I divide it into two parts where it intersects with H and H complement, and this part will be reflected, but this part, because it's a full map, it's still going to be identity. And lastly, I have the Mobius transformation, which is also conformal map, so I would have this 2 integral, and with y, which are just the spherical harmonics. So I would have just n's here. Okay. So I would have, that's why I have these n here on the right-hand side. So my volumes are divided into two parts, which intersects with h and which intersects with the complement. I'm just considering interior and then take it to the reflection. So what happens is that both of this volume, so I'm considering two parts in the in the big spherical cap, is that both of them, the spherical cap, the bigger spherical cap and the small spherical cap, it's like playing a game of how to find a balance between them. And what happens is that both of them, h or h complement, cannot be bigger than the original RPN. So I would have a strict inequality here. And the last line, I have to still control this volume somehow, right? The volume of the RPN under this compositions of a map. And the last line is bounded by a -1 conformal volume of phi. Remember, since phi is a minimal emergence, I can control it with its conformal volume. And where the conformal factor was this lambda1 was the RPN and lambda1 of Sn. And so what happens is that I would actually get 2 times of the conformal volume of RPN. So that's how I get the last quantity. Okay. Any questions so far? Okay. So I wanted to explain why I cannot get I could not get the conjecture that I had, was that because I don't know, if you look at this volume, I want to know that if I know where my orthogonality happens exactly, right, in the homotopy, meaning that what's the volume, if I know the exact upper bound of each volume, then I would be able to get the bubbling phenomena. But since I said the vector field just vanishes at some point, I don't know where exactly the orthogonality happens. That's where I would just get the upper bound of 2 projective spaces. Okay, but I did want to say some about the conjecture, is that there are some evidences that I tried to work on to imply that the sharp about the sharp upper bound is that, so I just calculated some of the scenarios where the parameters move around, and I just calculated some volumes, is that when the full map degenerates, so given n-dimensional embedded smooth surface, I'm just considering everything in Euclidean space, so I would have the Hausdorff measure of this volume under the fold map, and then I consider what happens when the fold map degenerates. So what happens is that, if you think about it, is this embedded surface, this larger part stays the same, but the complement part gets reflected. And if you consider this small part, if you make the full map degenerates, that means that the larger cap gets bigger and bigger. This small part gets reflected to the other side. And when it gets infinitely small, you're going to have a straight line that gets reflected to the other side, right? And that means you're just going to have, what happens if you reflect a split straight line? You're just going to get a circle. And that's what it comes here, the Hausdorff measure of the sphere, with the original volume that I had. And that was the scenario that I was thinking. And another case is, so I considered a different scenario when Mobius, what happens when Mobius transformation degenerates is that, so when you have a sphere, right, you have a curve, right? And if you try to push all of my curve to a point, right, what happens is that it's going to get smaller and smaller and smaller, and then it will get squashed to a point, right? Which is something that's not useful. However, the only interesting case that would happen, let's say I have something anchored at the South Pole, and I have a curve that's looking like this, and let's say my x goes to somewhere on the North Pole. Because it's my South Pole, it's still gonna be anchored at that point. However, you make the curve close to the North Pole, and in the end, what's gonna happen is just gonna get the volume of the sphere, and that's gonna be the best scenario, which is not the conjecture that not the quantity that I thought about in my conjecture, but yeah. So some results related to higher eigenvalues is that for lambda k in RP2, this also Karpik proves that a disjoint union of real projective space and k minus 1 identical round spheres with the same ratio of radii, and this bubbling phenomenon happens. Same thing happens for the two sphere. You're just gonna have k spheres. And PhDs recently also showed that under a certain Palais-Smale condition is that kth eigenvalue will be, for the compact dimensional manifold, is maximal with the sequence of metrics that converges to that of the bubbling. So this bubbling phenomena is something that happens in other, it happens for the sphere and projective space, at least in the surfaces. Okay, and so it's safe. That's why I had such a conjecture. Okay, for the remaining part of the talk, so I'm working on Richard Laugesen for another applications of this topological degree theory about Robin on the Robin boundary problem. So if you consider a Robin eigenvalue problem for a bounded Lipschitz planar domain omega inside R2, we have eigenvalues lambda depending on omega of the domain, of course, and alpha over L, which is the parameter of the Laplacian for which, so I'm looking for eigenfunctions that is not identically zero, satisfying these two equations. So Robin boundary problem, it's well known that it's like a linear combinations of the Neumann boundary and Dirichlet boundary, and alpha over L is what dictates the scale between them. Here, L is the length of the boundary, and alpha is the Robin parameter, and it is well known that for lambda 1, it's maximized when you have a degenerate rectangle goes to the segment, line segment. And for lambda 2, you have, it's maximized when you have a disk, right? And for lambda 3, for lambda, so it is known for minus pi to, when alpha is inside minus pi, between minus pi, 4 pi and 0, you know that you can consider this scenario for -1, this centered at -1 minus epsilon, and this centered at 1 plus epsilon, and you take this epsilon goes to 0, then that's where you're going to have this upper bound. So applying that reflection symmetry argument and try to get the orthogonality. So we extended the result for the positive side. So negative parameters was shown by Gerard and Laugesen, and it will be on the archive soon. This result, and Karpukhin and Stern in their paper as well, they can apply their method. They believe their method can be applied to this problem as well. And so what happens is that you would have for lambda 3, the equality is attained asymptotically if you make epsilon approach to 0. And yeah, so then the upper bound will be a disjoint union of the two disks. Okay, that was another application for the reflection symmetry arguments. Okay, that is it. Thank you.
Thank you very much, Hanna, for the talk. So I believe we have time for some questions. Feel free to unmute yourself if you have some. We already had quite a few during the talk.
So I have another question, Kim. Sorry, Hanna. The new bound for Robin is up to 4 pi, right?
Yeah.
And what is the preventing from going further than 4 pi?
I understand that it has it's something has to do with the eigenvalues differ when the parameters change, and I actually don't know about that part a lot. I'm still trying to understand, but I understand there is like a large history behind how to compare trial functions and eigenfunctions like that. Yeah.
Thank you, Alexandre.
I'd have a question as well. So in the case of either eigenvalues on the closed two-dimensional sphere, or for the Steklov problem, simply connected domains, if you look at higher eigenvalues, not just so there's these results where you get chains of kissing spheres rather than So I guess the question is two-sided. First of all, in terms of your upper bounds, if you're looking instead of lambda 2 at lambda 3, 4, 5, so on and so forth, can you build trial functions that would give you good upper bounds of a similar nature as the two kissing sphere, the k kissing spheres to optimize them?
Exactly. That's I thought about it for a while, and that will probably come to a lot of questions involving combinatorics as well, because you have to choose. There will be multiple intersections, and you have to consider now more than different choices of spherical caps as well. So yeah, that part I haven't. I'm sure there's a way, but yeah, I haven't been able to actually figure that out. Yeah.
And I mean, I guess the same question, but with the simpler geometry of the Robin problem that you're considering. In this case, do you think that in this case it might be easier because it's dimension 2 to get something similar again for lambda k?
Maybe because I'm not sure about I think it will probably be with the same problem with the selection process, but I actually can say the reflection symmetry part that actually works for any alpha, but it's just that like trial functions and eigenfunctions, those comparison just doesn't work. That part Yeah, so that's why we cannot extend further than 4 pi. Yeah.
Well, so I think we can thank the speaker again either way and start continuing questions if we want to afterwards. So thank you, Hanna, again. And we meet again next week with a talk by Yannick Montenot, which title will be available later in the week. So yeah, have a lovely week to everyone.
Thank you, Anna. Thank you, everyone.